All right, welcome. Let's dive into one of the biggest challenges in the world of gypsum science. How do you make boards stronger without just making them heavier? Well, the answer, it turns out, is in this critical and often overlooked area, the interface between the paper and the core. Today, we're going to break down the hard shell strategy. It's a really clever set of engineering techniques designed to do exactly that. So let's just start with the core problem, right? The engineer's dilemma. The whole industry is pushing for lighter, more efficient building materials. So how do you and I boost performance? We're talking especially about nail pull resistance, without just packing more mass into the board. It's that classic strength to weight problem that, every gypsum scientist is trying to crack. And the solution is this really elegant concept called the hard shell strategy. See, instead of making the entire board dense, which would make it heavy, you strategically place that strength only where it's needed most. And that's right at that high-stress boundary between the paper and the gypsum core. What you end up with is a deliberate, engineered density gradient. So how do we actually build this hard shell? Well, it really relies on two pretty distinct approaches. The first one is chemical. It's all about using the physics of drying to our advantage. The second one is physical, where we actually redesign the manufacturing process itself. So let's break them both down. Okay, first up is the chemical shell. This is all about leveraging the power of something called starch migration. This is where we get to turn a pretty simple additive into a really high-performance structural component, all through some clever chemistry and process control. So, what is starch actually doing in there? Well, at its most basic level, you can think of it as a binder, kind of a chemical bridge. As the board dries out, the starch molecules form this glassy solid that literally glues the interlocking gypsum crystals directly to the paper's cellulose fibers. But here's the trick. For this to work, the starch can't just hang out in the core, it has to travel. So as the board goes into the kiln, water starts evaporating from the paper surfaces. This creates this incredibly powerful capillary pull, which draws water and the starch that's dissolved in it from the center of the board outwards. It's this process that concentrates the starch exactly where we need it. And what's really cool is that we can actually predict and control this movement using something called the Pecklet number. You can think of it as representing a battle, a tug of war between two forces. On one side, you have advection. That's the bulk flow of water pulling the starch to the surface. And on the other, you have diffusion, which is just the starch's natural tendency to spread out evenly. So how do we tip the scales in this battle? Well, a high Pecklet number, which you get through faster drying, means advection wins, hands down. The starch gets swept right to the surface, and it forms this dense, really powerful glue line that is perfect for nail pull resistance. On the flip side, if you dry slower, diffusion gets to play a bigger role, and the starch ends up more evenly distributed, which we don't want for this. Now, controlling this migration isn't just about kiln temperatures. It's also about controlling the starch itself. We can actually fine-tune that Pecklet number by engineering the chemistry of the starch molecule. It's pretty amazing. Okay, so our main choices here are acid-modified and oxidized starches. Both are what we call thin boiling, which just means they have a low viscosity that helps them move through the core. But oxidized starches have a really key advantage. They help prevent something called clay shock, and that's the sudden problematic thickening of the slurry that can happen when clay impurities in the gypsum react with other additives. Molecular weight is this really delicate balancing act. It's kind of a Goldilocks situation. If the starch molecule is too big, it just gets trapped in the gypsum crystal matrix and never even makes it to the paper. If it's too small, it migrates way too easily and can form this skein that traps steam and causes blisters. So the goal is to find that sweet spot, a modified starch with the absolute perfect molecular weight for both mobility and bonding strength. Okay, so that was the chemical shell. Now let's switch gears completely. Let's go from chemistry to pure mechanics and process engineering. Our second technique is all about building a physical shell, using what we call high-density skins. The concept here is just wonderfully direct. Instead of relying on migration, we are physically applying a separate, much denser layer of gypsum slurry right onto the paper. Think of it like applying a thin layer of armor plating to the interface before the lightweight foamed coarse slurry even shows up. And this isn't just some theory, There's a major patent on this technology, and it gets really specific. It says this concentrated layer has to be at least 1.1 times denser than the core, it has to have a certain thickness, and it has to be formed from its own unique slurry. It even mentions adding fibers to improve the slurry's rheology, which is basically just a fancy word for its flow characteristics on the line. Okay, so that brings up a huge question, right? How in the world do you actually manage two completely different slurries, one dense, one foamed, on a production line that is moving at hundreds of feet per minute? Yeah, this is a massive process engineering challenge. Your standard setup just won't work. You need highly specialized equipment that can create, manage, and then deposit two totally distinct slurry streams at the same time, and with incredible precision. The patents and the literature show us three main ways this gets done. The simplest is using something called a flow splitter on a single mixer, which just diverts some slurry before the foam gets injected. A more advanced option is using a secondary mixer in a series. And for the absolute maximum amount of control, you can use two completely separate, independent mixing systems. Of course, each one has its own trade-offs in terms of complexity and cost. So let's just pull it all together for a second. The hardshell strategy really gives us two powerful complementary tools. On one hand, you have the chemical shell. It's driven by the physics of drying, and it creates a powerful adhesive glue line. On the other hand, you have the physical shell. This one is driven by process mechanics, and it physically lays down a structural armor plate. Both of these techniques achieve the exact same goal. They create that strategic density gradient for stronger, lighter board. Mastering them gives us an incredible amount of control. But it also raises this big question for the future. Now that we've figured out how to engineer the perfect shell, is the next frontier for performance hiding inside the core itself? What new chemistry or physics is going to unlock that next level?